potential divider. The potential divider is principle is used when you have a circuit which has two or more resistors connected in series with a certain voltage or EMF source. And the potential divider principle allows you to divide the potential or the EMF in a way that is directly proportional to the value of the resistance in the series combination. Okay, let's look at this simple circuit here to illustrate this point. I have got the EMF source of 12 volt here on the left hand side with little or no internal resistance, and connected in series with this EMF source I have two resistors, R1 and R2. This value is 4 kilo ohm, and the one on top is 6 kilo ohm. Right, let's look at the potential across each one of them, which I call it V1 on top and V2 on top. Now it's straightforward to calculate the value of the potential across each one of them. Firstly, the potential across R1 is simply the current multiplied by R1, where the current is given by the EMF divided by the total resistance value. Okay, so substituting I into here will give me the general formula for the PD across the resistance R1. And if I substitute the values inside, I will get a value of 7.2 volt. Now, similarly, I can apply this same kind of same current equation and apply it to calculate the PD by multiplying I to R2, and I get the formula of R2 over the total resistance times the EMF source. And substituting the values inside, I will get 4.8 volt. In fact, the sum of 4.8 and 7.2 gives you back the total value of 12. In fact, once you have done the first answer, the second answer can be calculated directly by subtracting away from 12 volt. Now, what's important about this simple problem is this equation here, which I'm circling now. As you can see from here, V1 is calculated from the ratio of R1 over the total resistance, and V2 is calculated from the ratio of R2 to the total resistance. Okay, so this, you can recognize this equation easily. So if I extend this idea to any number of resistors in series, you can appreciate this potential divider concept quite easily. If I call it R1, R2 and R3, and the total PD is E, then the PD across here is simply R1 over R1 plus R2 plus R3 times E, and PD across R2 will be R2 over R1 plus R2 plus R3 times E, and finally for R3, R1 plus R2 plus R3 times E. Okay, I hope you can recognize the pattern here. So the potential divider principle allows you to quickly write down the PD across each resistor by taking the resistance over the total resistance multiplied by the total PD across the entire chain of resistance in series. Now you can see from here, obviously the one with the larger resistance will get a bigger share of the potential. The one with the smallest resistor will get a smaller share of the total PD. So as you can see from here, this is 6 out of 10, this is 4 out of 10. So obviously the 6 out of 10 will get a bigger share of the voltage compared to the 4 out of 10. So this is the idea behind potential divider equation. Let's move on to look at the calculations in example 9. I have two resistors in series, and one end is connected to a terminal of potential of 3 volt and the other one is negative 15 volt. Now to calculate the potential difference between to calculate the potential at point X, you need to work out the potential difference between the two ends first. Now first of all, the difference in PD, potential difference, is It's not 3 volt or it's not 15 volt, but rather 18 volts. Okay, the 3 volt drops down to 0 and drop by another 15 volt to become negative 15 volt. So the total potential difference is 18 volt. So the PD across the 300 kilo ohm resistor is simply 300 over the total resistance. Now we have not included the kilo ohm because it appears in both the numerator and the denominators. And this is your 18 volt here, which I mentioned earlier. And you get 6.75. But 6.75 volt is the potential difference. It's not the potential. The potential at X is 3 minus 6.75. Or you can also calculate it as minus 15 plus 6.75 volt. Not 6.75, sorry. Plus 500 over 500 plus 300 times 18. Okay, that's another way of calculating the potential at X. Minus 15 plus 500 over 800 times 18, and that gives you 90 divided by 8, 1.125. 11.25, and that gives you the same value of minus 3.75 volt. Okay, so that's another way of calculating from the bottom or from the top. So essentially, if I can draw a vertical line here, this is 3 volt, it goes down to 0 volt, this is minus 15. The potential difference of 6.75 below here, this is the potential we're calculating at point X, 6.75 or 11.25 above minus 15 volt. Okay, so this calculation is obtained from subtracting 6.75 from 3 volt. This answer is obtained from adding 11.25 volt to minus 15 volt, but it gives you the same answer. Right, the next example. This diagram again shows two resistors in series and connected to the 25 volt here. We are to find the limits of potential difference where there is a variable resistor here. This is the variable resistor. The contact X can be adjusted. So yeah, to find the potential V, the VPQ between Q and X, where X is can be connected from here or from here, the lowest point. Now obviously if you bring X all the way to the top, upper end, then the PD between PQ is simply 4 divided by 4 plus 6 times 25, which is 10 volt. That's the first part. But if X is brought further down at the lower end, then there is no resistance within PQ. The resistance of PQ is simply 0. Okay, so in that case the PD across PQ is 0. So this is how we can vary the potential difference between 2 points by using the variable resistors. Next example, we have a 20 volt battery with an internal resistance of 2.5 kilo ohm, rather high value. It's connected to a 50 kilo ohm device and in series with the ammeter, which has no resistance, and there is a voltmeter connected across both the 50 kilo ohm and the ammeter. Now this is the diagram shown below there. That's what you need to draw. Right, you're asked to find the reading on the voltmeter and the ammeter. Now, first of all, you need to recognize that the 50 kilo ohm and the voltmeter of 120 kilo ohm are connected in parallel, and this combination actually creates a new resistance compared to the case when there is no voltmeter. So the voltmeter actually introduced some kind of change to the circuit resistance. So without the voltmeter, it's simply a 50 kilo ohm in series with the battery and the internal resistance. With the voltmeter in parallel to the 50 kilo ohm, things become different. So the first thing we like to do is to calculate the combined resistance of the voltmeter and the device, which is the inverse of 50 kilo ohm and 120 kilo ohm, and you get a value of 35.3 kilo ohm. Now with this 35.3 kilo ohm, we can now treat the whole circuit as if this is a 20 volt in series with a 2.5 internal resistance and a 35.3. This whole lot is what we calculated earlier, 35.3 kilo ohm. So the PD across the voltmeter is now calculated from the potential divider equation. Just 35.3 divided by 35.3 plus 2.5 times 20 volt, which is the EMF of the whole circuit, and that gives you 19 volt. And the current through the voltmeter, through the ammeter or the 50 kilo ohm, can be calculated by simply taking the voltage divided by the total resistance, which is 0. Now this current is actually the total current through both. This is the total current, not the current through the. This is EMF divided by the, or this current that I write here. 0.529 milliamp is the total current flowing through the battery. But the junction where the voltmeter connects to the resistor, the current actually splits into two paths. One path goes into the resistor, the other path goes in through the voltmeter, then they recombine back. Okay, but they have a common potential. So the way to calculate it is actually using the ratio of the resistance. Now, an easier way to see it is if I call this the current V and this is current R, I equals to I R plus IV, and 19 volt is a common potential. 19 volt, which I can write 19 is given by IR times the resistance of 50 ohm, 50 kilo ohm, and it's also given by IV times the resistance of 120 kilo ohm. Okay, I solve this, I should be able to work out the ammeter resistance, which is given by IR. Sorry, this is 0.529 milliamp. Okay, so from these two equations, I can find any one of the currents flowing through either the voltmeter or the ammeter resistance.